So while mass spectrometry allows us to determine the percent abundance of certain isotopes in order to determine the average atomic mass for an element, photoelectron spectroscopy actually allows us to determine the electron configuration of an element and therefore identify an element. So really quickly, just as a review, the further an electron is from the nucleus, the lower its ionization energy is going to be. And so we use that fact in order to look at this graph right here. So if you look at this, notice ionization energy, we also will sometimes call it the binding energy. It decreases as you move from left to right. So since it decreases, that means that the peak furthest to the left has the greatest ionization energy, meaning it's the closest to the nucleus. So what's really cool about a PES is you literally are just reading out the electron configuration as you go, because keep in mind, when you start with the electron configuration 1s, that's the closest to the nucleus and lowest in energy. Okay? And the only other thing you have to know about a PES is that the height of these peaks represents the relative number of electrons. So if you notice right here, the very first peak, that's going to be 1s. And so since I'm continuing on, I know it has to be 1s2. The next peak is going to be the next electron configuration. And notice it has the same height. So this is going to be 2s2. The next peak is going to be 2p6. The next peak, notice it's as tall as the 2s, so it's going to be 3s2. Then the next peak, 3p6. And then finally, the last peak is half as tall as the 3s2, which tells us it's going to be 4s1. Okay, so that tells us that that is going to be potassium. So it's a really cool technique because it lines up perfectly. It's showing you each of the individual sublevels, right? It's showing you the electron configuration. So just as a review, what it's counting on is the fact that those 1s electrons are the hardest to remove because they're the closest to the nucleus. Meanwhile, the 4s is the easiest to remove because it is the farthest from the nucleus. Okay? So let's look at this example right here. So it gives me 3 different peaks. So I start with this first peak. That first peak is going to be 1s2. I know it looks taller than the previous problem, but it's all relative. So that's going to be 1s2. The next peak is going to be 2s2. And the last peak, because it is half as tall as the other two, it's going to be 2p1 because this is 1s2, 2s2, 2p1. So the element is boron.
So I'm going to talk about one other key thing that you can look at with respect to a PES. So what you see right here is the PES for potassium. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So that's for potassium. What if I ask you to take the PES for potassium, for example, and using it, then draw the PES for another element? So for example, calcium. Well, if you think about it, calcium is 1 over from potassium. Okay, it's an alkaline earth metal. And so what distinguishes calcium from potassium is 2 things. First of all, calcium has 1 more valence electron than potassium does. It has 2 valence electrons. It also has a higher ionization energy because keep in mind, as you move traditionally, the trend is as you move from left to right across the periodic table, the ionization energy increases, and as you move from top to bottom, it decreases. So how could I use the PES for potassium to anticipate the PES for calcium? Well, I know that all of its ionization energies are going to be higher. That's one thing I know. So all of the peaks for calcium are going to actually be to the left of those for potassium. And the reason why, if you notice here, normally when we see a graph, it goes from 0 and it increases. But if you look at the graph here, notice the ionization energies are decreasing. And so that's why all of the peaks for calcium are going to be to the left, because all of its ionization energies are higher. Since it has a higher effective nuclear charge, its ionization energies will be higher. So this is, if I were to ask you to draw the PES for calcium, it would look like this. So I'd have a peak here. It's going to be the same height because it still has 1s2. 2s2 is going to be the same height, but it's going to be to the left because it has a higher ionization energy. It requires more energy to remove that electron. It's 2p6. It's going to be the same height, just to the left. And obviously this is just an estimate. Those aren't the exact ionization energies. its 3s2 is going to be to the left. Its 3p6 is going to be to the left. Okay. But keep in mind, for the last peak, I had said the two differences in these elements is number one, their ionization energies. Calcium has a higher ionization energy, but then also it has one more valence electron. So I am going to draw the peak to the left. However, it's going to be twice as high as potassium's peak because it has two valence electrons while potassium only has one. So quick review. Here's my PES. Keep in mind ionization energies for PES decrease, right? Therefore, if I'm comparing elements, if I have PES for one element, I need to compare their ionization energies. If the element has a greater ionization energy, all of its peaks will be to the left of the element that has a lower ionization energy. And the exact opposite is true if you have an element with a lower ionization energy. Okay, so if I had an element that had lower ionization energies, all of its peaks would be to the right.